Okay, today I'm gonna start to talk about power in AC circuit. Um, so at the beginning, I will go through all the theories, background to see how the power in the how we calculate the power in AC circuit, and then uh, uh, after that we'll look some examples. So to begin first, assume that we have a circuit um, like this. So it's connected to the source, the voltage source, and then it comes here and connected to a resistance, and then it's connected to some kind of other elements, some loads, like is going to be, for example, the capacitance or inductance or something like that, and then it goes back to source, something like that. Now, if you assume the source that we have in, in phasor format, it has uh, the voltage of Vm or V max with angle of 0. So, um, so it's going to be our Vm. And then we have a current going through this. Assume that. So I'm going to also put it Vm instead of Vmax. So it's a So this is the Vm, or the actually Vmax, and then we have the I that is going through here. So it's going to be I. Um, so the V is this. This is going to be the I, and I show you how we calculate that. Then we have the R here, as we have, and then here we have, for example, the combination of inductor or capacitance, something like that, and then it's going to have going to be Jx, something like that. So the combination of these two, because they are in series, we know that if we have two elements in series, we can go ahead and say the equivalent one of these two is like that. We um, actually add them together. So I would say that it's going to be uh, the Z. The impedance is going to be R plus Jx, and then we can write it in the polar format as the magnitude of Z with angle of, assume it has angle of theta. So assume we have something like that. So we have the source, resistance, um, some kind of reactance, like the, as I said, inductance, capacitance, and this is what we will have. So the very first thing that we can calculate here is we want to calculate this I here. So if I go ahead and say, uh, uh, we know that we can say the V is Zi. So therefore I can go ahead and uh, rewrite that, um, or replace that. So here I have the Vm with angle of 0 is equal to Z, which is going to be the Z with angle of, let me put it in parentheses, so it's going to be Z with angle of theta, and then we have I, so it's times I. So therefore the I, what we have, the I is going to become uh, Vm with angle of 0 divided by Z with angle of theta. So now if I calculate, that's going to be as I said, is in polar format, so we can divide the magnitude and subtract the angle. So it's going to be the Vm divided by z, and with angle of 0 minus theta. And if I call this Im, just the maximum, assume here I call this term assume this is going to be equal to Im or I max, then I can go ahead and say that the I is equal to Im with angle of negative theta. So I can go ahead and write it here. So the I is going to be the Im with angle of negative theta. So this is what we have in this condition, that if we assume this is going to be like that. Remember that here I assume the theta for the V is 0, but later on we show that it's going to, it doesn't matter whatever angle we consider, that it's going to be the relative, the angle in the current relatively is going to change. So just merge, so the theta, that this theta that we have here is basically the difference between these two. So if it is the volt, the theta at V, minus the theta for the I. So it's the theta for the I, this is the theta for the V. Here we put the, in this case, we assume the theta for the V is 0, so theta for the I is going to be negative theta. But it's always like that. The theta is going to be the difference of theta V minus theta I. So we will show that later on how we use them. So now assume this is the circuit we have. We have circuit like that, and we have these three elements in our circuit, and they want to work with us. So I'm going to write them here again. So we have the V is the V max with angle of 0. So this is the source voltage at the source. Also the voltage at the equivalent of these two. The current is the maximum current with angle of negative theta, and the impedance in the system is going to be Z is equal to magnitude of the Z with angle of theta. So these are the three equation that we have, or three relationship we have for this specific circuit. Now that we have these three, I want to go ahead and start to calculate the power for three different conditions. What if only we have a resistance in this system? So this part is 0. What if we have only an inductor in the system? So there is no R, there is no capacitance. So R is 0, the capacitance is 0. What if we only have the capacitance? So there is no R, the R is 0, and the inductance is also 0. And then we calculate the voltage based on this value, the power based of these three values for each of them. So let's go to new page. So here, the very first case that I want to work for that, so we're going to calculate the AC power for I would say if only we have a resistance. So for a resistive load, I would say resistive load. So only if we have a resistance in the system. So there is The L is 0. There is no capacitance. There is no inductance uh, in in the system. So what we have basically there in previous one here, the X is 0. This this Jx here is going to be 0. There's only R in the system. So if there's only R in the system, what we are going to have, so the V that we know, the V is V max with angle of 0. That's what we know. And for the so that is the V that we have. For the I, we know that the I is going to be the I max with angle of negative theta. So to find these two, this one, we know the angle, but we know to find the theta. So we know the Z is going to be the magnitude of Z with angle of theta. And if we only have R, so we have only R. So because we have only R, the magnitude of Z is going to be R. And we know that when we have R the Z, the impedance for the R is just R with angle of 0. We know that when we have only R, this is the impedance for the R. Is the R itself with angle of 0. So therefore, it will tells me that theta is going to be 0. So if I compare these two together, the theta is going to be 0. Now that I have the theta is equal 0, I can go ahead here and write that in time format. So I can go ahead and say V is T is the maximum V cosine omega T plus 0, but the angle is 0. I'm going to just write it here, so plus 0. The same here, the IT, I convert it from phasor to time, so it's going to be Im, the maximum I, the cosine omega T, again, and this is the negative theta, which is 0. Again, it's plus 0 because theta is 0, so it's going to be like that. Now that I have these two, I can come here and calculate the P, and I know the P, the power, is just time V T times IT. Just multiply these two together. So it's going to be this time, this one, multiply this one. So it's going to be V max cosine omega T, and I don't write the 0 because I do not need it, times I max cosine omega T, and I don't write the 0 because you don't need to have it there. So if you do this, it's going to be the V max, I max, and then cosine square omega T. So this is going to be the PT that we have here, the power. And this power is going to be the instantaneous power. So it's basically tells them by changing the time how the power is actually changing. So this is the so it's the instantaneous power that we have. So it's a time-dependent power. And if we calculate the average value of that over the time, if we go ahead and calculate it, the average of that over the time for the is going to be the this Vm Im divided by 2. So it's going to be its average over time. So if we have a pure resistance in the system. There's nothing but the resistance in the system, and we have the AC source. This is going to be the power that we are going to get in the system that we have. Now let's go ahead and look at what would happen if we have for only we have an inductor in the system. So we'll say the AC power for an inductive load. So means that there is no resistance, there is no capacitance in the system. Then what would we have in this case? Again, I'll go ahead and write the V, the voltage. We know the voltage is the maximum voltage with angle of 0. That's what we have. And the I was the maximum I with angle of negative theta. So again, I have to find that. So here I know that the Z is the magnitude of Z with angle of theta. So here, because we have only inductance, so we know the ZL, if it's only inductance, is going to be J omega L, or in other words, going to be equal to omega L with angle of 90. So if I have this and compare this with this one, then I know that theta is 90 degrees. Now I can use this and go and write this as a time domain. So the Vt is going to be the maximum of V and the cosine omega t plus 0, and then the It is going to be the Im cosine omega t, and then plus negative theta, which is going to be negative 90. So because the theta is 90, so negative theta is negative theta. So this is the Vt and the It I have. Similar to the previous step, again, the instantaneous power is Vi time, Vt times It. So again, if I just go ahead and use these two equations here, so it's going to be the Vm cosine omega t, and don't write the 0, times Im cosine omega t minus 90. And if you go ahead and do some trigonometry calculation, eventually it will comes out as Vm Im divided by 2 sine 2 omega t. So this is going to be the instantaneous power if we have the only the inductive forces. So if there is only inductive force, this is what you are gonna get. For this one, if I calculate the average one, the average one, it will comes out as 0, because it's look at here, because it's I will show you later on the graph, but because it's a sinusoidal wave, so the average of that is going to be 0, in contrast with the previous one that it was for the resistance force, because it's a cosine square, so it's always going to be positive. Here in inductance force, because there's no square sign here, so it's going to be negative positive, so it's going to be the sinusoidal wave, and its average would become 0. And And the very last one that we want to look for that before we go to the general case is that what if AC power for um, if you have the only the capacitance in the system. So AC power for the capacitive force. So only we have the capacitance in our circuit. What would happen? Again, I would go ahead and write. So the V, the voltage is the source voltage. So it's going to be the Vm with angle of 0, the maximum of V with angle of 0. The I, we know that's going to be the Im with angle of negative theta. And the Z is the magnitude of the Z with angle of theta. So because it's only we have only capacitance, we know that this is going to be the ZC, and we know that's going to be negative J over omega C. So this is a this is what we have, and sorry, J over omega C. So this is the so this is the Z that will so that's what so, and then it is going to be equal to, otherwise it's going to be 1 over omega C with angle of negative 90. If I write this with in the polar form, so if I compare these two together, it will tell me that theta is negative 90. The theta is going to be negative 90. And then if I come here, I can write them in the time format. So it's going to be the Vt is equal to Vm cosine omega t plus 0. And here I'm going to have the It is going to be the Im cosine omega t plus the negative theta, which is going to be plus 90, because negative theta is negative, so it's going to be plus 90. And then when we have it like that, so I can go ahead and then write the instantaneous power is going to be with Vt times It. And if I go ahead and do the calculation, so it's going to be the Vm cosine omega t, so I don't write the 0, times Im cosine omega t plus 90. And then if I do the calculation, eventually I would get the negative Vm Im divided by 2. That's going to be the sine 2 omega t. So if you look at here, the difference between this one and the one that is for the inductance is this one's the is going to be negative here. So it's going to be, you will see it's negative in the inductance, which was previous was the positive. This one is going to negative, and the same as the inductor, the average one is going to be 0 because it's the sinusoidal wave. So if you average it, again, it's going to comes out as 0. So these are the 3 cases that we have for the, if you have the pure resistance, pure inductance, and pure capacitance. So what happens if there's nothing else but one of them in the system. So these are the instantaneous power and the average power for each of these 3. And as you will see, only the resistance has the average power. The other 2 has the 0 average power. By the way, so before I go ahead and show you the how these things gonna be, if I replot it, how they look like. Just know that if we have the power is positive, when we're talking, if the power is positive, is basically we will say the power is absorbed. So we say the power uh, um, absorbed or used, basically. So if the power is negative, means the power is uh, supplied. So basically, um, for this, we know that when we say for that in the resistance, the power is always positive and is always absorbing the power, always using the power. For the sources, the power is always negative because it's always supply the power. And when it comes to the capacitance and inductance, you see that because they have a sinusoidal form, it's going to be positive, negative. Positive, negative means that in one cycle they store the energy, in the next cycle they release the energy, in the next cycle they store the energy, in the next cycle they release the energy. So that's why the average energy consumption is zero. So let me go ahead and show you how these plots look like. So here you can see how this power is going to look like. So the first column is if only we have a resistance in the system. The second column is if only we have a um, inductance in the system. And the third column is if we only have a capacitance in the system. So if you look at the first column, um, um, the top graph in the first column. So we'll see that there's a voltage and current. So the first row is voltage and current. The second row is the power. So the first image, so the first column, first row, the image at the very top right, top left corner. So we'll see that the voltage and current are actually in the same phase. So wherever the voltage goes up, the current goes up. Whenever it goes down, the current goes down. So they have the same phase. Um, as you can see it here. But if you look at the top row, the middle image and the right image, you will see there is a um, difference between the current and voltage. Either the current is leading or the current is um, lagging the uh, voltage in, for example, in these two cases. So they are either 90 degrees ahead or 90 degrees behind. So the current is either 90 degrees ahead or 90 degrees behind the voltage. So you can see it on the top two, um, on the top row, the middle, and the right image. Now, if you look at the bottom row shows the power in each of these for each of these conditions. So if you look at the power row and the very left image, which is for the resistance, what you would see here is that you will see the power is always positive. So it goes from the very maximum value, it goes to zero and goes back to maximum, goes back to zero, goes to maximum. So it's always positive. And it means that in the resistance, we always use the energy. So because it's positive means that the resistance always absorb the energy. It because it's not negative means that the resistance never ever can provide the energy. It only absorb the energy. If you look at the bottom row, the middle figure, which is for the inductor, you will see that in the middle figure for the inductor, the power is in half cycle positive, the other half cycle negative. Then it's positive, then negative, positive, negative. On the half cycle that it is positive, it's actually absorb the energy or store the energy. In the other half cycle that is negative, it's release the energy, it's or it's stored in the previous half cycle. So it's store the energy, release the energy, store the energy, release the energy. So eventually you will see the average energy it stores and release is going to be 0. The same here, if you look at the bottom row and the very right image is for capacitance. The same thing is here, but the only difference that first here it is stored. If first it release, then it store, release, store, release. So whenever it is positive, it stores the energy. Whenever it's negative, it's release the energy. So in the capacitance, so it's store the energy, then the next half cycle it releases it. The next half cycle is store it. The next half cycle release it. The difference that's here in inductance is stored and as a magnetic field. In the capacitance, it stores as the electric field. Again, it's the same as a capacitance. You see, over the time, the negative positive is going to cancel each other. So the average is going to be 0. So the average for the resistance, which is the very, still I'm talking about the second row. So the very left image, which is in the second row, which is the resistance, has some average energy consumption. But when you look at the inductor and capacitance, the middle and the right image at the second row, the average is 0. So they only store and release, store and release. They are not using or providing any energy. Now let's look at what happens if we have the general case. So up to this point, we assume we have only resistance, only capacitance, or only inductance. So let's see what would happen if we have general cases. So the combination of any of these can be present in the system. So the AC power for general load, in this case, I would say that it can be combination of any of these three, can be combination of the resistance, capacitance, or inductance. If we have this again, what we have here, we know that the voltage was the maximum voltage with angle of 0, and the current was with the maximum current with angle of negative theta. So this part we know that, and we know that this is the general load, so it has the impedance of Z with angle of theta. So if I go ahead and this time we'll just write it in the format it is. So the VT is going to be the maximum voltage cosine omega t plus 0, and then the IT is going to be the maximum of the I cosine omega t minus theta. So these are in the time format. So now if I want to write the instantaneous power, so PT is going to be the VT times IT, which in this case is going to be Vm cosine omega t. So I'm not going to write the 0, and then times Im cosine omega t minus theta. That we have here. And if we go ahead and do some trigonometry and do some calculation, eventually the instantaneous power for general load would comes out as the Vm Im divided by 2 cosine theta time 1 plus cosine 2 omega t and plus Vm Im divided by 2 sine theta cosine sine to sine 2 omega t. So it's going to be the general instantaneous equation of that, and so it's the time dependent, or this is going to be the instantaneous power. If we average this equation over time, if we average this over time, we said this terms is the cosine, so it's going to be 0. This term is also sinusoidal, it's going to be 0. So if we average it over time, what would we get would be the average would be Vm Im divided by 2 over cosine theta. And if we replace this Vm and Im with the root mean square and do the calculation, eventually you are going to have the root mean square of the V, root mean square of I, and then cosine theta that we are going to have, and it's going to be in watts. The units. So the units would be in watts. So when it comes to the average sources that we were talking here about, that we know that the average force is going to be only positive, only available for the inductance, for general load. So if I go ahead and if I want to write for the average, so the average AC power, that what we have is that the P for if we have the resistive load, so for if I have only resistance in the system, for resistive load, the P average is positive. So if you have the resistance, it's going to use the energy, it's not going to provide the energy. For source, if I have a source, the average energy provided by source is going to be negative. So the sources always provide the energy. For inductive force, for inductive load, the average is going to be 0. The same for capacitive load. For the capacitive load, the same here, the P average would be 0. So we know that when we are talking about the average, this is only going to be usually when we are talking the average load, we are only talking about the resistance. So how much the resistance actually consume energy for whatever we have. So also I'll just write the equation again here, which was the VRMS IRMS cosine theta that we have, and we know that for the VRMS is maximum of the V divided by the square root of 2. The same, the IRMS is the maximum of the I divided by the square root of 2. So this is the value. So this value only is positive for resistant force, and it's going to be 0 for uh, inductor and capacitor. And I will talk about the theta a little bit later. So this is the average AC power. So if we talk about it, so the instantaneous power was this that we have it. This is what happened over time. This is the average AC power that we have. Another power that we have that is related to actually the capacitance and inductance, although the average power they're using is 0, but there's going to be the power in those loads. So the next one is going to be the reactive power. The reactive power. So the previous was the average power. This one's going to be the reactive power. And for the reactive power, we will call it the Q. And it's only related to inductor or capacitance in the system. And it's going to be VRMS, IRMS, root mean and it's going to be the sine theta that we are using. The unit for this one is still it has the same physically they have same magnitude, but to be make sure that this reactive power is not going to get confused with the average power or the power itself, they use it as the they call it the var. So the unit is var, or is basically is the volt. It's a volt ampere volt ampere reactive. So for when we are talking here, it's in watts. The units of this is watts. The units of that is called var, and it just uses that rate, as I said, to make sure it's not going to get confused with the average power or instantaneous power. So the reactive power. So again, for inductive load, if you have the inductive load, the Q is positive. So the magnitude of Q is going to be positive. If you have the capacitive load, the magnitude of Q would be negative. And we have resistive load, the magnitude of the Q would be 0. So for these three conditions. So if you have the inductive, it's going to be positive. If we have the capacitor, is going to be negative, and if we have the resistive, it's going to be 0. So it's called the reactive power, and as you can see, is the power that is only related to the inductor or capacitor. It doesn't have anything to do with the resistance. So for the resistance, when you're talking, we only talk about this average power here that we have. So you see, it's going to be 0 for the other two. When we have the inductor or capacitor, we have only talk about the reactive power, and for the resistance, going to be 0, so we don't have it there. And then we have the combination of these two kind of that we can consider, which going to be the apparent power. And power, which is going to be the combination of the previous two one that we have. So we have the average power and we have the reactive power. Now what we have here, the apparent power, I just show it with the S. A square is equal to the average power square plus the reactive power square. So it's gonna be like that, and its magnitude, if you do the calculation, is gonna be the VRMS IRMS square. And for the unit of that, again, it's gonna be call it as the VA, which is the, again, to be make sure it's not being confused with the other two, it's going to be volt ampere. So it's going to be volt ampere. So it's a volt amp, basically. Uh, uh, what we have. So this part, as again said, this average part, we only have it for the resistance. So it shows the power, what's happening for the power in your resistance. This reactive part shows that what's happening in your capacitance or inductance in case of the power. And then this term shows, if you put them both together, what would be happen if you have them both together. Now that we have these three, so I want to go ahead and talk a little bit about uh, the theta that we have, and then so if we talk about the theta and see how we can use it. So if I go ahead and say, so the angle that at the theta that we talk about it, and it's going to be usually they call it the power angle. Up to this point, we assume the theta v is 0 and the theta I is negative theta. But in general, theta is the difference between the voltage angle minus the current angle that we have. So if I write it in general form, so let me go back and write it a little bit general form. If I go say the V that I have is the Vm with angle of theta V instead of 0, and the I is the Im with angle of theta I, then theta is going to be theta V minus theta I. So in all cases up to this point, what we did is that we assumed this one is 0, so the theta was the negative and the theta I. But so it's a general format. So whatever you consider for the theta V, there's going to be you are going to get the theta as going to be okay. So what we have here for the theta is that this theta can have a couple of conditions. So if the theta is 0, what does it mean? It means that what we have is pure resistable. So if the theta is 0, then we have pure resistive load. It means that we only have a resistance in the system. If the theta is 90 degrees, then we have the pure inductive force. We have only an inductor in the system. So we have the pure inductive load, means that there's only an inductor in the system, there's nothing else. If the theta is negative 90, it means that we only have the capacitance in the system. Capacitive load that we have. If the theta is going to be between 0 and 90 degrees, so if let's say the theta is between 0, so if it is 0, it's going to be resistive. So it's going to be between 0 and 90 degrees, or also it can be equal. So what we have is going to be the inductive inductive load. The general behavior of the load we have is like the inductive load. If it is going to be between negative 90 and 0, the general behavior load that we have is going to be the capacitive load. So these are the angles. And by the way, this theta is going to be between negative 90 so it's going to be between negative 90 and 90 degrees. So this going to be the magnitude of the theta. And when we have this, and there's another thing that we call it is they call it the power factor, and write it here. So if I calculate the cosine theta, so let me write it here. So the RS is that's the power factor, and the power factor would be equal to the cosine theta, which is also equal to the ratio of the average power to apparent power. So this is going to be called the power factor. So if we know the theta, we can calculate the cosine theta and find that power factor as well. So basically the power factor shows the ratio of the power consumed by the resistive load in the system compared to the total power in the system. So now that we have this, the next thing that I will talk about them is going to be the power triangle. So the power triangle. So in the power triangle, we are going to visually show the resistive, the average, the power related to the resistance, the power related to the inductance or the capacitance, and the apparent power in the system. So the first case is that if we have the inductive load, load, and for the inductive load means that also we call it the lagging load. If you hear that, it means that the same thing. So inductive load or lagging load. In this case, we talk about if we have the inductive load, the theta is going to be between 0 and 90 degrees. So we know that the theta is going to be between 0 and 90. If it becomes equal to 90 degrees, which is pure inductive load. So that's what we have here, and the theta is also, that's the difference of the angle, the phase in the voltage minus the phase in the current. So this is the first thing we know. So we know the theta is going to, and we know that for the inductive force, the Q, the reactive power is also positive. So this is also what we know. So these two. Now the average power is always positive, so we know that. So we are going to use the horizontal axis to show the average power. So it shows that this is going to be, let me choose 3 columns. So it's going to be, assume this is going to be the P average, the magnitude of the P average. And then, for example, assume this is the Q. I draw the Q on the vertical axis. So it's going to be the Q. And we know that in this case, the Q is going to be positive for the inductive load. And then the apparent one is going to be this one. So it's going to be the S. And as you can see here, this is going to be the theta that we have it, and then we can see here also the same. The S square is the P average square plus Q square. So this is it. And so also you will see here the cosine theta. The cosine theta, which is the power factor as well, is going to be the P average. The P average divided by apparent power, which is also is going to be the power factor as well. So this is the triangle that we have it here, and we can use it to do the calculation visually. So it usually make it easier to just looking at that and try to work with that. The second part is that, so I'm going to draw a line here. The second part is if we have the capacitive load, or also they might call it the leading load. It's going to be the same thing. So the leading load, again, we know that when we have the capacitive load, the theta is going to be between negative 90. It can be equal to 0, between negative 90 and the same. The theta is theta V minus theta I. And we know that in this case, the Q is going to be negative if we have the capacitance in the system. So now if I go ahead and draw that triangle again, so the P average is still going to stay the same. So it's going to be horizontal one. So it's going to be the P average. And then the vertical one is going to be, I draw the Q on the vertical. This one time is going to be negative. So it's going downward. So it's going to be the Q, which is negative. And then I'm going to have the S that goes from here to here. So it's going to be the S. Similar to that, again, you can see the S squared is a P average squared plus Q squared. And then again, this is going to be the theta here. This time is negative because it's rotating clockwise. So it's going to be negative here. Again, the same, the cosine theta is going to be the same as we have it in this case here. So the cosine theta, so you can calculate it from the P average divided by S. But remember that the theta is going to come negative this time when we are dealing with it. So here the theta is positive, theta is negative. Also, sometimes we may need to use the tangent of the theta, because the tangent is going to be Q over the P. So if I also write it here, the tangent theta is going to be the Q divided by P average. The same, you can write it also here. So the tangent of theta can be, again, Q. It's the Q divided by P average. So usually we use this triangle to do the calculation between these three, and it helps us to do the calculation visually. It's much easier to do it this way, and so you can actually see what you're doing. So draw, whenever you have it, draw the average power, which is related to resistance in the horizontal line. And if you have the inductor in the system, or you're dealing with the inductor, just draw the Q positive. If you are dealing with the capacitor, draw it negative, and then connect it to get the apparent power in that case. Next thing is that some simple power, so AC power relationship. In addition to other equation that I gave you up to this point, we can also calculate the power from the following equation that I give you. So if we have the Z in the system, is going to be the with the magnitude of the Z, an angle of theta, or in other words, you can write it as a R, which is going to be the resistance plus Jx. And if I consider this part as a representing the resistance, and this part the X and the sign, both of them together. So X with its signs, the X with its signs is going to consider it as a reactance. If we consider this, we can and we know that we know that the for resistive load, for resistive load, X is 0. For for inductive load, the X is positive. For capacitive load, the X is going to be negative. So we consider the X with its sign here. Now, if we consider that, then we can write for the P average, which is only related to the resistance, is going to be the root mean square of I. We can write it as that times R, or it can be written as voltage at the resistance, the root mean square of that divided by R. So the voltage at the root mean square of the voltage at the resistance, the square divided by R. The same for that we can write for the Q. So again, the Q is going to be the IRMS to X, and the same here also we can write it as a similar to what we have here, the voltage of whatever is the impedance or capacity is inductor or capacitor, whatever the voltage it has, the RMS value of that to the power of 2 divided by the X. So that's going to be the X. Remember that in these two cases here, for both these two cases, keep the sign. So if it is going to be the inductor, is going to be positive. It's going to be the capacitance is going to be negative. So the values comes out as a positive or comes out. You know that the Q for the inductance is positive, and for the capacitance, the Q for the capacitance is negative. The P average that is always positive. So we can also use these two sets of equation in case to calculate any of the average or the reactive power as well. The very last thing that I want to mention in theory is that how we can write the AC power in the complex format. So the AC power in complex form. So how we write it as a complex form. So if I go ahead and write it, the apparent in the complex form, the apparent power can be written as half of the V and then I star. This is how we can write them. Or let me start from V and M. So if I write the V, it's going to be the V max with angle of theta V. And I write the I, it's going to be the I max with angle of theta I. If I have that, then therefore the I star is going to be the I max with angle of negative theta. So it's going to, the magnitude is the same, just the angle is changing, the sign of the angle. Then the apparent power is going to be half of V times I star. So this is how we can write it in a complex format. So if we have this and times them, this is what we are gonna get. So also we can go ahead and substitute these two here and do the calculation. So if I do that and do the calculation, so you will get the value one. So whatever that you have, so we have the V in the complex format, the I star in the complex format, and then it's going to be the S, and this is going to be equal to the P average plus JQ. So if I write it there and then from convert it to the rectangular format, it's going to be the P average plus. So I can say that the P average is the real part of apparent power, which is going to be the real part of this. And the same here, the Q is going to be the imaginary part of the S, or is going to be the imaginary part of the VI square. So VI star. So we can also do the calculation. If we need to, we can do the calculation in complex format. Sometimes it's going to be easier to convert everything into complex and calculate the, as here, calculate the apparent power from this equation and rewrite it into rectangular format, and then uh, find the average and the reactive power from that complex format.